Predicates and Quantifiers. Definition. Let P of x be a statement involving a variable x, and let D be a set. We call P of x a propositional function, or predicate, if for each D from the domain D, P of D is a proposition. We call D the domain of discourse of P of x, or just the domain. Example, P of x is x squared plus 3 is an odd integer. D is the set of all positive integers. The proposition P of 2 is true because 2 squared plus 3 is 7, and 7 is odd. P of 5 is false because 5 squared plus 3 is 28, and 28 is even. Definition. P of x, let P of x be a propositional function with domain D. The statement for every x P of x is said to be a universally quantified statement. Symbolically, it may be written as this. Here, this symbol is capital A rotated upside down. So we read this for every x P of x. This upside down A is called universal quantifier. The statement is true. The universally quantified statement for every x P of x is true if P of x is true for every x in D. So this symbol is read for every, for all, for any. All of these three readings are the same, mean the same. Example, P of x is x squared plus 3 is an odd integer. D is z plus. The statement for every x squared plus 3 is an odd integer is false, because we already know there is at least one x for which this is false. For example, x equals 1. 1 squared plus 3 is 4, which is even. Another example, P of x is if x is greater than 3, then x plus 2 is greater than 5. The domain is the set of all real numbers. Symbolically, we can write P of x this way. If x is greater than 3, then x plus 2 is greater than 5. For every x P of x means for every real number x, if x is greater than 3, then x plus 2 is greater than 5. This statement is true. Let x greater than 3 be true for some x. Then x plus 2 greater than 3 plus 2 is also true. We just set 2 to both sides of this inequality. We get a true inequality. So we have if true then true, which is a true conditional proposition. That is, we show that if true then false cannot happen, regardless of what is the selection of x, as long as x is greater than 3, then the other inequality is also true. Another example. Let p of x be a propositional function with finite domain of discourse x1 and so on xn. The universally quantified statement for every x p of x is the same as this conjunction p of x1 and p of x2 and so on and p of xn. The next definition, let p of x be a propositional function with domain of discourse D. The statement there exists x such that p of x is said to be an existentially quantified statement. Symbolically, it can be written this way. This symbol, it is capital E rotated 180 degrees. This symbol is called existential quantifier. There exists an x such that p of x is true if p of x is true for at least one x from D. So this symbol, existential quantifier, is that they exist, there is, it means the same. Example, p of x is x greater than or equal to x squared. The domain of discourse of x is a set of all real numbers. What is the truth value of the proposition? There exists an x such that x is greater than or equal to x squared. If we select x to be 0.5, then 0.5 is greater than 0.5 squared, which is 0.25, which means that there is an x such that x is greater than or equal to x squared. This is true proposition. The next example has the propositional function has domain of discourse R. What is the truth value of the proposition? There is an x such that if x is greater than 1, then x over x squared plus 1 is less than 1/3. If we select x to be 3, then 3 is greater than 1, so this is true. This with x replaced by 3 becomes 3/10 less than 1/3, which is true. If true, then true is true. So we found that a value of x for which the conditional proposition is true, which means that the existentially quantified statement is also true. Let P be a propositional function with a domain of discourse x1, x2, and so on, xn, finite domain. The existentially quantified statement for there exists an x such that p of x is the same as the disjunction of these n propositions. P of x1 or p of x2 or and so on, or p of xn. Theorem, De Morgan's law for quantifiers. if P is a prepositional function, each pair of prepositions in A and B has the same truth value. In A, we have this pair. The negation of for every x P of x, there exists an x such that not P of x. And the second pair is this. The negation of there is an x such that P of x for every x not P of x. Why? The prepositions in the first two prepositions in A, the two prepositions in A have the same value. Assume that the first preposition is true. The negation is true, so it is not the case that for every x P of x. This means that there is at least one x for which this preposition is false. Which means there is at least one x in the domain for which the negation of P of x is true. So if the first proposition is true, we figure out that the second proposition is also true. If the first proposition is false, this means that for every x P of x is true, so that it is not the case that for every x P of x is true, which means that at least for one x in the domain P of x will be false. That is, the negation of P of x is true for that x. So we see that there is at least one x such that not P of x is true. This theorem generalizes the De Morgan laws. Negation of conjunction with P and Q is equivalent to not P disjunction not Q, and negation of disjunction P or Q is equivalent to not P and not Q. Write the negation of the proposition. Every student at FSU is taking a math class this semester. Symbolically, this statement is for every x P of x. The P of x is the propositional function. X is taking a math class this semester. The domain of this course is the set of all students at FSU. The negation of this is it is not the case that for every x P of x, and the generalized De Morgan law says that this is the same as there is x such that not P of x. These are equivalent, but we will read the last one. In words, it means there is a student at FSU not taking a math class this semester. Precedence of quantifiers. The quantifiers, universal and existential, have a higher precedence than any other logical operator. For example, there is an x such that p of x or q of x means this. We have parentheses here rather than this parentheses here. The part of the logical expression to which a quantifier is applied is called the scope of the quantifier. So the scope of the quantifier is just p of x if the expression is written this way. In this example, there is an x and then p of x or q of x in parentheses. The scope of the quantifier is the whole expression, and we say that the variable is bound in p of x and in q of x. Any occurrence of the variable that is outside of the scope of the quantifier is free. In this example, there is an x such that in parentheses x greater than 2 or x squared less than 7. This is a proposition because there is not a free variable. That is, x is bound in both expressions. Well, here there is an x such that x is greater than 2 and or x squared less than 7. Here only the first x is bound in the function x greater than 2, well, the x in the function x squared less than 7 is free. So the whole expression is still a propositional function because there is a free variable.